Mr. T here. This video, Chemical Reactions and Conversions Part 3, will cover chemical reactions. We're going to investigate balancing chemical reactions, making sure the reactant atoms and the product atoms balance each other out. We're then going to get into chemical calculations that goes by the fancy name stoichiometry, where we convert, like we did last time, molecules and grams to moles, and then we're going to go from one substance to another. So molecules, for example, of substance A will be converted into molecules of substance B using a balanced chemical equation. Then we're going to get into one of the more popular applications of stoichiometry, limiting reactants. You'll see this in actually every major science class. They love limiting reactants type of problems. Then we're going to get into miscellaneous calculations that you have to master, including calculating percent yield, percent composition, empirical formula from percent composition, and calculating a molecular formula. So let's go ahead and begin. We're going to go ahead and start getting into chemical reactions and then balancing. So iron rusting is an example of a chemical reaction. We started with iron and oxygen, and then it formed iron oxide. Now you can already predict the product from this from the reactants in a chemical reaction. So if we started off with iron and we started off with oxygen, then you can predict iron to oxide. So the first thing we do is we go ahead, because it's a combination reaction, as we figure out the single ions from the starting reactants. So iron plus, and then here is a O2 minus for oxide ion. Now, it turns out it's a variable ion, which makes it more complicated, so it's not a plus, it's a 3 plus, because technically there's only two types, 2 plus and 3 plus. And so we had to infer what the, it requires some prior knowledge. This is a little bit more challenging of a problem compared to the representative ions I've showed you earlier. But my point is this. We're able to go ahead and use our charge balancing rules, so CBR, charge balancing rules, and figure out a charged balance product. So with a iron 3 plus and oxygen 2 minus, excuse me, I have to raise it higher. We're going to go ahead and need the least common multiple, which happens to be 6. There's going to be 2 of the iron 3 pluses that are needed, and there's going to be 3 of the 2 minuses of the oxides. So the final charge balance product is going to be Fe2O3. Now again, this was a little bit harder problem because it required prior knowledge of what the iron variable ion was going to be, and I'm not going to give you a problem like this if I ask you to predict a combination product. But what we're now going to get into is balancing. So you'll notice that in the starting reactant, there is only 1 of the iron atoms, whereas in the final product, there was 2 of the iron atoms. So this is where we get into balancing a chemical equation. Here's carbon and oxygen in a chemical reaction, forming carbon dioxide. As far as counting the number of atoms, there's 1 carbon. Over here on the product side, there's 1 carbon. There's 2 oxygen and 2 oxygen, so this one is actually balanced to begin with. we talked about the various equation writing symbols. There's the physical state symbols, arrow, and then we have the addition, which just means one substance versus another. It separates two or more formulas. And I just showed you the number of atoms for the reactants equal the number of reactants from the equal the number of product atoms. So this equation is balanced when we count the number of atoms. Here's another problem. Here's our aluminum. Again, that one's easier, one that I could test you on. If we look at the single charges, then we have aluminum 3 plus, sulfur 2 minus, and then this right here is the charge balance product, aluminum sulfide, which is seen right here. Now, you'll notice that when we start counting the number of atoms, we have 1 atom versus 2 atoms. So now we need to balance the equation. We do this by adding in coefficients. So there are our coefficients. The coefficients are multipliers. And they multiply the number of each of the atoms within that species. So 2 for the aluminum, 3 for the sulfur. So what we're going to have to do is we're going to have to come up with a equation balancing grid in order to figure out the proper coefficients to go in front of each of these. So these coefficient grids will allow us to figure out what coefficient multipliers are going to go in front. So let's go ahead and practice this. I'm going back to the outline, and because this is so important, I've included examples on the outline. If we scroll down, there's our balancing chemical equations. You'll notice that I'm taking the same exact problems from part 2. Matter of fact, these already have charged balance products. So I literally copy and pasted it. Now I'm going to go ahead and modify this just a bit. I'm going to modify this question and say complete the equation predicting the charge balance products for the double replacement reaction of the reactants below. And I'm going to go ahead and get rid of equation balancing with coefficients not required. Now they are. Now you still are not responsible for writing the physical state symbols, but now you're responsible for equation balancing. So I'll make a little comment down there, and equation balancing. In the first step, you went ahead and had to predict the charge balance products. In the next step, you have to go ahead and I'll use a blue pen, is go ahead and create a nice atom grid in order to show the reactant atoms and product atoms. So this is what I do. I go ahead and name the species in front. There's magnesium. There's oxygen. I then put in parentheses how many magnesium there are. There's 1 magnesium. There's 2 oxygen. This is the left-hand side of the reaction arrow. These are all reactants. On the right-hand side, we match up the magnesiums. this is going to be 1 magnesium and 1 oxygen. Now we need to go ahead and put in the multipliers to figure this out. I'll go ahead and I'll use a green pen. So in this case, we put a 2 right in front. That multiplies both the magnesium and oxygen. So there's the 2. Then there's the 2. So on the right-hand side, we have 2 magnesium, 2 oxygens. Now we have to go on the left-hand side. On the left-hand side, we have the oxygens. Those have been balanced out. There's 2 and 2 on each. However, the magnesium is not balanced out, so we have to stick a 2 in front. So 2 times 1 is equal to 2. So now, the magnesium atoms are balanced out on each side, and the oxygen atoms are balanced out on each side. Let's go ahead and scroll down again. Now we have to use our imagination. We're going to complete the equation predicting the charge balance products, and this has already been done. Aluminum sulfide has been predicted, and now we need to go ahead and equation balance. So I'm going to pull out my blue pen again, and I'm going to go ahead and set up my my atoms. Now, instead of breaking everything by atoms down, in my opinion, it's better to break it down by ions. So this is where we count the number of ions. That just kind of makes it a little bit easier, especially when we get into something called polyatomic ions. You'll have the same results as the atoms. Matter of fact, when you start breaking things into ions, for polyatomic ions, it'll make it much easier. But let's go ahead and pretend that we're breaking everything down by ions. So here we have aluminum, and we're just going to keep that 3 plus charge. That charge has nothing to do with equation balancing, although it will make it easier down the line again for polyatomic ions. There's the sulfur. So we go ahead and we break it down. We have 1 aluminum. We have 2 sulfides. If you go on the, oops, that's aluminum by the way. If you go on the right-hand side, there are 2 aluminums and then 3 of the sulfides. So we need to go ahead and try to balance this out. So, and this may require that we have to redo some of our answers later on. I'm going to go ahead and put a 2 here for aluminum. 2 times 1 is 2. And that balances out the aluminum. And then I need to go ahead and start putting in numbers for the sulfur. So let's see. I could always do this. 3 times 2 is 6, so I put a 3 there. And then I'm going to go ahead and place a 2 on the other side. It's 4. And then 2 times 3 is 6. So this doesn't require that you play around with it. If we go ahead and we take a look at our sulfides, those are balanced out. So we have 6 sulfides, and then we have 6 sulfides, and then we have 6 sulfides on the product side. So let me say it again. 6 sulfides on the reactant side, 6 sulfides on the product side. Let's go back up to the aluminum. That's not balanced. However, if I were to sit there and change this, so that there's 4, then I'll change this one over here. So it's going to be 4 times 1 is 4. So 4 aluminums on the reactant side, 4 aluminum ions on the product side, 6 sulfides on the reactant side, 6 sulfides on the product side. This equation is now balanced. We're all done. Let's do the next one. Again, breaking it up by ions. So magnesium 2 plus, fluoride minus. There is a, let's see, starting 1 for magnesium. There is 1 for fluoride. And then we have to include copper, which has a plus and a chloride. And I'm writing down the ions even though they don't make a difference at this point. Let's see, 1 copper, 1 chloride for the reactant side. Did I make any mistakes? Yes, I did. This one right here has 2 fluorides. Let's go with the right-hand side. There's 1 magnesium. There's 2 chlorides. There's 1 copper and 1 fluoride. Now let's go ahead and start putting in our values. We need to go ahead and see if the magnesium are balanced out. Yes, magnesium are balanced out. Are the fluoride balanced out? No, so I'm going to go ahead and put a 2 here. Now that means putting a coefficient right in front of copper fluoride and has to multiply both copper and fluoride. So automatically you have to put a 2 in front of the copper ion, and we have 2 and 2. We start from the beginning, magnesium balanced, fluoride's balanced, copper's not balanced. Now we go to the other side. We go ahead and we put a 2 here. Again, it multiplies the copper and chloride. So there's the copper, there's the chloride. We start from the beginning. 1 for magnesium, balanced. 2, it's balanced for fluoride. 2 balanced for copper. 2 balanced for chloride. We are done. So let's do the next one. I'm going to go ahead and show you one with polyatomic ions. And we pretend that the many atoms that make up the polyatomic ion is just one species. So for example, carbonate ion, even though it's CO3, we consider it one species. So we just put a 1 right here. So we do the same pattern as we did in the previous examples. So we have 2 sodium, 1 carbonate, 2 hydrogen, and 1 sulfate. And then 2 sodium on the product side, ions, 1 carbonate, 2 hydrogens, and 1 sulfate. So the sodium are balanced out, the carbonate are balanced out, the hydrogen are balanced out, the sodium are balanced out. So we have a 1 to 1 to 1 to 1 ratio, as it's already balanced. That one's pretty easy to do. If you want to, the 1 can be implied, or you can include the 1s. It doesn't matter. In this case, I'll just go ahead and I'll arbitrarily include the 1s, but they can be implied. Let's go to the next one. I broke it down by ions already, down below. So looking at the iron ion, there's one of the reactants, one of the products. Notice how it's already balanced. I'm going to speed up now. We have 3 chloride reactants and 1 chloride reactant or 1 chloride product. So I'd go ahead and I'd start putting 3 here. I have to put it up in front. That's a multiplier that multiplies both ions. So it multiplies the ammonium ions for a total of 3, and it multiplies the chloride ion for a total of 3. Now we start all over again. 1, 3, 3. Now let's go to the ammonium side. Notice the ammonium and nitrate are not matched up. So I'll put a 3 right here. So 3 times 1 is 3, 3 times 1 is 3. Now the ammonium nitrates are balanced out on both sides. So it's a 1, 3, 3, 1 ratio. And in this case, the 1s are simply implied. Let's do the next one. Again, I already broke down by ion or polyatomic ion below. So the reactant and product silver ions are already balanced, cyanide's already balanced, gold's already balanced on both sides, and nitrate's already balanced. So you can write it like this, or you can just put a 1 to 1 to 1 to 1 ratio. Either one. In this case, I'll just arbitrarily choose not to include the 1s, and they're implied. So I'll make a little comment on there. The 1s are implied. Let's go back to the slide. Here's slide 10. So there is a starting problem right here. You'll notice that the number of hydrogens on the left-hand side doesn't match with the number of hydrogens on the right-hand side. So therefore it's not balanced. If it's not balanced, not all ions are balanced, then you will need to go ahead and start putting in coefficients. Now this is the textbook and the slides example right here. It's nice and neat. Instead of putting the equal sign over here and say equals 4, they just summarize it to the left-hand side, and that's okay. Another way of doing the exact same thing. So here's another example. They broke it down by atoms, and then they put in the coefficients in order to balance it out, in order to balance, as we see right here. Again, the 1s are implied. They could have also put 1 and 1 here, but that's optional. So here are examples for you to work with. And then here are bigger examples with polyatomic ions. So this is a bigger one, or bigger ones that I could test you on. First off, you can tell that the number of magnesiums on the product and reactant side are not balanced, so it's unbalanced. So we need to have a reaction diagram that you see down here. Now slide 15 already has a worked out problem that includes polyatomic ions. This is a double replacement reaction. The slide showed you part of how it's broken down, but I still want to take you through the process. So I set up a ion table that you see down below, and then we need to start putting in our numbers. So the first thing I would do is I'd go ahead and I'd put in a 3 here, so that way the magnesiums are balanced out. Notice by putting in a 3 here, I have to multiply not only the magnesiums but also the chlorides. Now I start from the beginning again. The magnesiums are balanced out, the chlorides are not, so then I have to go into the right side. I put a 6 here. This allows us to balance out the product chlorides with the reactant chlorides. And keep in mind, it's a multiplier, so it multiplies everything across the species. So it multiplies the sodium as well as the chloride. So 6 sodium, 6 chloride ions. Start over again, 3, 6, 6. Notice how the sodium is not balanced out. So then I have to go to the other side, and I have to put a 2 here. 2 times 3 is 6, because it's multiplying not only the sodium, but the number of sodium ions you have. So 2 times 3 is 6. And then it multiplies the other species as well. So 2 times 1 phosphate equals 2 phosphate. So now everything is balanced out. 3, 6, 6, 2. So even for the bigger, more challenging double replacement polyatomic ions, you can still use an ion table to figure out the proper coefficients. As a reminder, 1 is optional. So before the magnesium on the product side, I can choose to put a 1, or I can leave it blank. Both are considered optional. And here are more examples on the next slide. Slide 16 that you can work through as well. Now we're going to go ahead and do stoichiometry. Stoichiometry is chemistry calculations. That's just a fancy way of saying it. And we're going to perform calculations from a balanced equation that we just learned how to do. So my first example will be the one that's on the example side of the outline. So you just kind of scroll down. So here is a balanced equation. The balanced equation that required charge balancing as well as equation balancing. This is the same equation that we determined from problem E. So now we're going to do a math calculation. We need to go ahead and start off with the moles, given whatever number that we have. So in this case, 30 moles of iron chloride, and then we need our target moles. Notice there are different types of species, iron chloride and ammonium chloride. So you need a balanced equation in order to convert it properly. You are going to use the coefficients in front, and the coefficients in front tell you the amount of moles needed for this proper chemical reaction. So for this reaction, we need 1 mole of iron chloride. We need 3 moles of iron nitrate, 3 moles of ammonium chloride, and 1 mole of iron nitrate. Now, we may not be using all of these species in the actual math calculation. In this case, we're only going to use these two right here, iron chloride, and we're going to use ammonium chloride. And we're going to use the numbers that are in front, 1 and 3. Keep in mind, if there's no number there, then it's implied. So we need to develop an equality. In this case, there's a ratio, a 1 to 3 to 3 to 1 ratio. So 1 mole of iron chloride is equal to 3 moles of ammonium chloride. So this is going to be used to create our mole ratio. We'll get into what a mole ratio is in a second. So we're now going to use the math patterns of unit analysis that we discussed in the beginning of the semester. And problems like these are the whole reason that we had to learn the math patterns in order to go from kilometers to miles or pounds to grams. We're applying the same math patterns in these chemical problems. Now, these chemistry problems mathematically will make no sense since you don't deal with them on a regular basis. So you know you're doing it correctly if everything cross-cancels properly. So automatically, moles of iron chloride needs to go on the bottom. And moles of ammonium chloride need to go on top. Now, this right here is a mole ratio, and the numbers in front are the ratios from the balanced equation. So in this case, it's going to be a 3 for ammonium chloride and a 1 for iron chloride. Now, these numbers right here are non-measured. So the only one that you have to worry about is the starting value in this case. In this case, it's going to be 2 sig figs. So you go ahead and do your calculation, and then it's going to give you 90 moles of ammonium chloride. Starting value has 2 sig figs, so the final value should have 2 sig figs. Notice the cross canceling. That's how you know you've set it up properly. Now, we've already learned that you can convert moles into grams and moles into molecules. So now we're going to combine what we learned in Chemical Reactions Conversions Part 1 with Chemical and Reactions and Conversions Part 3. So here we have iron chloride and ammonium chloride, same type of problems as before. So first thing we need to do is go ahead and use the balanced equation. We'll go ahead and we'll use that. There's our balanced equation right there. And now let's go ahead and do the rest of the problem. Now you're going to have to go from grams of your substance A to moles of your substance A. You'll then use a mole ratio to go to the moles of the substance B, a different substance, to grams of your substance B. So to go from grams to moles, you're going to need to use the molar mass, and you'll have to calculate that from a periodic table. And on a quiz or exam, I'll specify which one, or I'll give you the molar masses. And then to go from moles of A to moles of B, you're going to have to use a mole ratio that you determine from a balanced equation. And then from moles of B to grams of B, you're going to have to use another molar mass. So the starting value is iron chloride, so 5.0 grams of iron chloride. My advice as you do this is go ahead and set up a couple skeleton conversion factors in your unit analysis problem. Automatically, using our unit analysis pattern, we know that to cross cancel, the grams of iron chloride should go on bottom, and then it should be out of 1 mole of iron chloride. So in a separate process, you have to figure out the molar mass of iron chloride. Using my really cheap periodic table, it's going to be 162.2 grams of iron chloride. That value may differ depending on what periodic table you use, because different molar masses use different instruments, so they'll be slightly off. I then need to use a mole ratio. So same mole ratio as last time, since we're using the same species. So I'm just going to bring that over really quick. So 1 mole of iron chloride is equal to 3 moles of ammonium chloride. So I put the 1 mole on bottom, and then the 3 moles on top. Highly recommend you get into the habit of putting a box around this. This is the mole ratio that requires the balanced equation. Now we're going to go ahead and convert. Uh-oh, made a mistake. Should be ammonium chloride. Now we're going to go ahead and convert out of 1 mole of ammonium chloride, then grams of ammonium chloride. So I just put it in. And again, this is taken from my own periodic table, which might be different from yours. Make sure everything cross-cancels before you even start doing your math. Now I'm cross-canceling the units. Please keep in mind that when you go from moles to grams or grams to moles, it's always out of 1 mole. Always out of 1 mole. And the only time you ever use the different numbers is in the mole ratio. So in this case, there's 1 mole of iron chloride and 3 moles of ammonium chloride, so then that's where you have to put in different numbers for the moles. Now you go ahead and do your calculation. And my final answer is 4.9 grams of ammonium chloride. So sig figs matter. Starting value, always you count the sig figs, so 2 sig figs. You count the molar mass sig figs, so there'd be 4 sig figs. Mole ratio is non-measured, so that has infinite sig figs. And then the molar mass for ammonium chloride has 5 sig figs. So the least sig figs is going to be 2, so it should be to 2 sig figs. Here is your final answer, calculating the number of grams of ammonium chloride that will be produced in a balanced reaction starting with grams of iron chloride, and assuming all the other grams are properly accounted for. Now I'm going to do a similar problem. The only difference is I'm going to go ahead and figure out the number of molecules instead of grams of ammonium chloride. So what I'm going to go ahead and do is take a lot of the repeated work to demonstrate this. First off, we need a balanced equation. And then here is the balanced equation right here. And because we're dealing with the same type of species, we can use the same balanced equation. We also need to have a flowchart for our plan of attack. So the one thing I'm going to change is this portion right here. Where instead of grams, it's going to be molecules. And then instead of molar mass, we're going to use Avogadro's number, 6.02 times 10 to the 23rd. Now, the rest of the setup should be very similar, only we're converting using molecules at the end instead of grams. So here's the final setup and answer, where I've converted molecules using Avogadro's number. And here is our final answer, 5.6 times 10 to 22nd molecules of ammonium chloride. Now, it's going to be 3 sig figs because there's 3 sig figs and 6.02 times 10 to the 23rd. That is a measured number, so it really depends on where you get that measured number from, because there's different instruments to measure it. But in this case, I gave it to you. Now we're going to do one more. Only instead of starting off with grams of iron chloride, we're going to go ahead and start off with molecules as well. So maybe I'll say something weird. Instead of using a really large number, I'll use a regular one. So I'll say 35.00 molecules of iron chloride. Now, do need to erase the highlighter, and then there's the molecules, and there's the molecules. Now technically ionic compounds are not considered molecules just because of how they're structured together. They're not molecules because they don't have covalent bonds. So I am cheating a little. The technical word for these are formula units. Formula units. But I don't want you to worry about those little details at this point. I want you to focus on the math. So now, because I'm using the same species, I'm going to start salvaging from the previous problem. Here is a balanced equation that we're going to use. And then I'm going to start salvaging my plan of attack and overall setup and bring it over here. So here is the same plan of attack and the math setup. So I replaced the starting value of molecules of A, requiring a Avogadro's number up in the left-hand corner. And then my starting value is molecules. So therefore, I need to use Avogadro's number. Notice it's the same ratio since we're using the same balanced equation. And we're still converting it back into molecules of B. So we need Avogadro's number. And our final answer is 105 molecules. As far as sig figs goes, starting value has 4 sig figs. Avogadro's number in this case has 3 sig figs. And then the final answer has 3 sig figs as well. So your final answer should be rounded to 3 sig figs. Notice there's no 0 past the decimal point because then that would make it 4 sig figs. So that's stoichiometry. And this is the size that you could be expecting on future quizzes and exams. Let's now go straight to the slides and show you some more examples. So this is slide 23. You could be given a question like this, along with a balanced equation. So first things first, you need to make sure that you have a equality based on the balanced equation in order to do a mole-mole ratio. So this one's a pretty easy problem because you start off in moles. How many moles of iron are needed for the reaction of 12 moles of O2? So there's a 12 moles of O2. There is our ratio that we determined from using the coefficients in front of iron and oxygen. So 3 moles of O2 equal 4 moles of iron. Because we're starting off with moles of oxygen, then the moles of oxygen go on the bottom. We have 3 sig figs in our starting value, infinite sig figs for the ratio, so 3 sig figs in our final answer. Now, we assume that the mass of the reactants, in this case silver and chloride, is going to equal the mass of the products. In this case, silver sulfide. So we call this the law of conservation of mass. Now, with that premise, then we can automatically assume that we can convert from our grams into moles and then use a mole ratio. And then when we're in moles of our other substance, convert that into grams. So be familiar with the concept where the mass of the reactants equal the mass of the products, and then the rest of this is the same pattern that we just got finished showing you. So let's move on. In this case, we want to go from um, moles of our N2 into grams of ammonia. So we start off with moles, do the mole-mole ratio, also known as mole-mole factor, same thing. And then instead of ending in moles, we convert the moles of ammonia to grams of ammonia, also known as nitrogen trihydride. 3 sig figs on our starting value, 3 sig figs on our final answer, so the final answer should be rounded to 3 sig figs. Here's another problem, only this time we're going to go ahead and start off with the product moles, and they want to know how many grams of O2 are needed. Now, this stoichiometry stuff, it doesn't matter if you start with your reactant grams or moles, or whether you start with your product grams and you work backwards. It doesn't matter. The method is the same, and the process is the same. So you have to go from moles of your iron oxide into moles of your oxygen. So you need an equality between these two, and then you'll convert from moles to grams. So here's the setup. Starting value is 3 sig figs, infinite for the mole ratio, and then 3 sig figs for this molar mass, so your final answer should be rounded to 3 sig figs. Now we're going to do the harder one that we've already practiced. We're going to start off with grams, go to the moles, and then grams. Again, we're always going to be out of 1 mole whenever we use our molar mass. In this case, 3 sig figs and implied 3 sig figs. 3 sig figs here. We have our mole ratio, infinite sig figs because it's not measured, and then 3 sig figs in our final answer, so it should be rounded to 3 sig figs. Notice how everything cross cancels. And then here is another problem. We're starting off with grams of CO2, and we want to know how many grams of C2H2 is needed for this reaction to occur. Using the coefficients, we create a mole ratio, and we start off with grams of CO2, so we need the molar mass. Notice how everything cross cancels. And notice how whenever we have molar mass, it's always out of 1 mole. 1 mole. And then here is another problem. And another problem. And another problem. These tend to be mass to mass, but I could also give you molecule to molecule as I showed you earlier. So now we're getting into limiting reactants. To demonstrate the concept of limiting reactants, let's pretend we have this pseudo reaction right here where we need 1 cheese and 2 pieces of bread to create 1 cheese sandwich. So there's our cheese, there's our pieces of bread, and then here is our cheese sandwich. If I were to have 10 pieces of cheese and I were to have 20 pieces of bread, then I could make a maximum of 10 cheese sandwiches. Because keep in mind, it's a 1 to 2 to 1 ratio. So I always need twice the amount of bread in order to make the cheese sandwiches. Now, let's say, for example, that I only had 3 pieces of cheese and 20 pieces of bread. In this example, I have more than enough bread. Matter of fact, I would say that I have an excess amount. Whereas with cheese, I just simply don't have enough cheese to make the optimum amount of cheese sandwiches. So we call this one the limited amount. So the maximum cheese sandwiches I could make is 3 cheese sandwiches. I'd run out of cheese by then, even though I'd have an excess amount of bread. So this is the maximum yield that I can make. I cannot make more cheese sandwiches unless I get more cheese. We have another term for this. We always have two terms for the same thing. Another term for this is maximum theoretical product, or maximum theoretical yield. So you'll see those terms all for the same thing. Now, the starting term limited, because technically this is based off of a chemical reaction. Before the reaction arrow, technically these are all reactants. So there's a reactant, there's a reactant. So we call this the limited reactant. Whereas this is the excess reactant. Now, things get a little bit more complicated when we use grams. So I could go ahead and use a scale or a mass balance. We'll just stick with a mass balance. And I could go ahead and weigh the cheese and the bread on my mass balance and turn this into grams. And then we still have to figure out what the limiting reactant is and the excess reactant. We can't just reason it out by the numbers. So going to slide 39, we have the same pseudo reaction, only now we're looking at the mass for each. So given 200 grams of bread and 200 grams of cheese, what is the limiting reactant, excess reactant, and maximum theoretical product? So now I went ahead and I drew or sketched two different equations going from grams of bread to bread to number of sandwiches to grams of sandwich. And this is using the same stoichiometry that we just learned how to do. I have equalities up here. Please note I did change the equalities in the midst of this commentary. It won't look any different from your final handout that you printed, but there were some slight differences in like a few minutes ago. But bottom line is I use these equalities right here, allowing me to convert from grams of bread to bread, and then our sandwich to grams of sandwich. So I started off doing this calculation, and this gives me a theoretical product of 250 grams of sandwich with a starting amount of 200 grams of bread. Now this is assuming that we have enough cheese. Now I'm going to do a second calculation where I start off with 200 grams of cheese and then I convert to grams of sandwich the same way, using the same equalities that we have above, giving me a final answer of 1,000 grams of a sandwich. So you're going to be doing the exact same steps in a chemical calculation. The next thing you need to do is figure out which one of these is the limiting, which one is the excess, and which one is the maximum theoretical product. The smaller number is going to be the maximum theoretical product. I know it's counterintuitive, but it's the maximum that you can produce, since the starting bread is going to be the limiting reactant. Now, it turns out we have a lot more cheese than we need, so then the cheese is going to be the excess reactant. So in chemistry land, again, the limiting reactant is the reactant that controls the amount of products you can make. And the amount of products that you can make is the maximum that can be produced. The other product is excess. Even though technically you could create more product, there just isn't enough of the limiting reactant to make it. So you're going to have to, in chemistry land, go ahead and start off with your grams and convert to moles. You'll then have to go ahead and do a mole ratio to figure out the moles of your product and then convert it into mass. You'll do a second calculation for the other reactant. You'll then go ahead and figure out which is the least of the two products, and then that will be your maximum. So here's a problem. 25 grams of iron oxide, 25 grams of aluminum. In this case, I start off with grams of iron oxide, and I need to calculate the molar mass to go from grams to moles. So notice we're starting off with this one. Now if you have more than one product, it doesn't matter which one you choose as long as both of the starting reactants choose that product. So for example, we are arbitrarily choosing that we're going to find the maximum theoretical product for iron. So iron oxide and aluminum are both going to find it for iron. Now, I could have easily solved for the maximum theoretical product of aluminum oxide, but I chose not to. Again, it's just arbitrary. You get to choose which one. So once you're in, once you've gone into moles of iron oxide, you need to go ahead and use a mole ratio, and this requires that you have a supplied balanced equation. If one is not supplied for you, then you have to make it up. You have to take these starting reactants and predict a charge balanced set of products. This would be a double replacement, and then you'd have to go ahead and in a separate calculation, you'd have, or in a separate ion table, you'd have to figure out what are the coefficients for a balanced equation. Okay, so once we're in the mole ratio taken directly from the coefficients, we then have to go from moles to grams, just like we've practiced earlier in other stoichiometry problems, and that gives us our grams of iron oxide. Now we have to perform a second calculation, starting with grams of aluminum, and then we'd use the mole ratio after turning it into moles for iron, and then solve for grams of iron, and then there's our two problems. Now take a look. For aluminum, it's 77.6 grams of iron. If we take a look at the other problem, it's 19.4. The smaller number is going to be the maximum theoretical yield, or maximum theoretical product. So on bottom, it summarizes this. And then the starting amount, that's considered the limiting reactant. So that's the limited amount. And then the other amount is the excess reactant. Make sure you know which one is which, and you're able to label those. Here is an example of one all worked out. So given 10 grams of hydrogen and 10 grams of oxygen, what is the theoretical maximum product of H2O? Notice it's asking for the same thing. I could have said maximum yield or maximum theoretical product, different ways of saying the same thing, of H2O produced and the limiting reactant. Now I need to go ahead and set up two different equations. One with grams of hydrogen, go from grams to moles, use the mole ratio from the balanced equation, and then moles to grams, there's our theoretical product. We often say the word theoretical product because it's math. We didn't do it experimentally inside a lab. It's all the math of what should be present if we actually did the experiment. That's why it's theoretical. We then started with grams of oxygen, and then did the same process to figure out the theoretical product for grams of water. And then the smaller one is the maximum, and then the starting value is the limiting reactant. So let's go ahead and go straight to our outline. Here is our outline. So I have some examples below that we're going to work through now. So this is a limiting reactant problem. The only difference is in starting with grams, it's going to start with moles. So it actually has a little bit less steps. So you could be given a problem like this, where you have to start doing some extra steps. So in this problem, you have to go ahead and take the starting reactants and figure out what the charge balance products are and balance the equation. You'll notice I'm using the same starting reactants that I used from previous examples in the outline, just to give you an idea of how things work, since you've already been practicing this. So I go ahead and I predict the charge balance product, which is what you see in red pen. So I assume that it's going to be a double replacement reaction. I break it up into ions and then swap them. Afterwards, I have to do equation balancing in order to put in the proper coefficients, if any are needed. From there, I'm going to need to go ahead and figure out the limiting excess and maximum theoretical product. So I have to write two separate calculations. And I'm just going to arbitrarily choose, we're going to find the maximum theoretical product for ammonium chloride. I could have chose iron nitrate if I did both of them. Now in this problem, I'm doing something a little bit different. I'm starting with moles, so I can end with moles. So I don't have to convert from grams to moles, it's already been done. So you notice all we need in the box is the mole ratios. And then the smaller amount is a maximum theoretical product, and therefore the starting reactant is limited. So 30 moles, the limiting reactant is going to be 30 moles of ammonium nitrate. And then 30 moles of iron chloride is the excess. Now let's go ahead and do a similar problem to this, only we'll do the more traditional one where we solve for grams. So here we have starting reactants of iron chloride, 5.0 grams, and 5 grams of ammonium nitrate, 5 grams of iron chloride. Notice it's the same starting values that we used in the other stoichiometric calculations. First step, we need to go ahead and figure out what is the charge balanced, equation balanced product. So I simply repeated the work that you've seen earlier in order to come up with this. There's our balanced equation. Just like last time, you have to have two separate calculations, one from grams of iron chloride to one of the products. You have two to choose from. I just chose ammonium chloride, NH4Cl. So I went from grams to moles, used the mole ratio from the balanced equations, coefficients, and then once in moles of ammonium chloride, I went from moles to grams. I did the same thing with the starting reactant of ammonium nitrate. And as you can tell, the ammonium nitrate produced the maximum theoretical product. So it's the smaller value of the two, 3.3 grams of ammonium chloride. I then labeled 3.3 grams of ammonium chloride as maximum theoretical product, and the starting value, ammonium nitrate, is a limiting reactant, and then the excess is 5 grams of iron chloride. So make sure you know how to do these steps. Make sure you know how to master these steps. So just learn it but master it by practicing it over and over and over. So I'll let you go ahead and do this one now that you've seen the process for this. Let's go ahead and go on to some easier stuff. We're going to get into percent yield. Percent yield is the amount of the actual yield compared to the theoretical yield. So actual is the experimental, and that's when you're actually in the lab itself mixing the chemicals, and then you're using the mass balance to figure out the amount of product you get. Theoretical, that's all the math that we do on paper. So for example, going back an equation to this one right here with grams of hydrogen and oxygen. This right, oops, I guess that's a bad pen to color. I'll use a different one. Use a highlighter. This right here that I'm highlighting, this is considered the theoretical yield. So maximum theoretical product and theoretical yield are the same thing. So that's the theoretical yield. Now when you take the actual from the chemistry experiment inside a lab divided by the theoretical done from the math that we do times 100, that's the percent yield. Ideally, the experimental value should equal the math value. That's how you know you did a good experiment, and it should be 100%. Realistically, it may be below 100 or above 100. Below, maybe you just didn't produce enough product because there was errors in the experiment, or above because you have contaminants, which artificially increase the amount of product you have. And obviously it's contaminated. Make sure you go ahead and memorize this equation. So this is the percent yield equation. How would I test you on this? Well, I would give you the experimental or actual amount, and then I would give you the theoretical amount, and then ask you to do a simple calculation. Having memorized the formula, actual divided by theoretical, you then just go ahead and plug and chug it. And then that gives you your percent yield. Again, please keep in mind you could have any value. It could be less than 100 or it can be more than. The closer you are to 100, then the more accurate it is. So let's move on to the next one, called percent composition. Percent composition, also known as percent by mass, tells us the percentage weight of each of the elements within a molecule. So for example, it tells you how much the weight of hydrogen is inside H2O, or it tells you the weight of oxygen inside H2O relative to the other parts of the molecule. Now, this doesn't do too much for us in Chemistry 101 or 105, but it does allow you to do some really cool calculations if you take more advanced science. So this is more preparatory for your future science classes. But just to give you an analogy of a percent composition, let's go ahead and look at the gentleman down below. We're going to figure out the percent weight of each body part. So we we experimentally measured the weight of each body part. So the head is roughly 10 pounds. The arms are 20 pounds. Notice what I did was I added together the weight of each arm. So one arm weighed 10 pounds, the other arm weighed 10 pounds. Together it's a total of 20 pounds for the arms. And then A total for the legs is going to be 40 pounds, and then the torso is going to be 20 pounds. So there is a total weight of 90 pounds. That's LBS for pounds. Now we're going to figure out the percentage of weight for each of these body parts. So we take the individual one body part for like the head. We go 10 divided by 90 times 100. 20 divided by 90 for the arms times 100. Again, we're going to add together the total arm amount. We're not distinguishing between the left and right arm. Total amount for the legs times 100. And then total amount for the torso, even though there's only one, divided by the total times 100. And this gives us the percent body part weight. So here is the percentage by weight for each of the body parts. 11% for the head, 22% for the arms, 44% for the legs, and 22% for the head. Now we're going to go ahead and figure out the percent weight for each element within the molecule, regardless of how many atoms there are. So for example, let me just go ahead and do the highlighter really quick. Each hydrogen, so you can consider this 1 mole of hydrogen is going to be 1.01 grams. Because there's going to be 2 hydrogens that I am underlining, then it's going to be 1.01 times 2. So that's the total weight for the hydrogen element. If we take a look at the total weight, that's where they have 1 mole of hydrogen, which is 1.0 grams. They have another hydrogen, 1.01 grams, and then they have the oxygen. And using their crude periodic table, it's going to be 16.00 grams. And so the total weight is going to be 18.02 grams, which is where they got this bottom number. So you take the top total element mass divided by the molecular weight, or molar mass for the water, times 100, and then that's the percent by weight for hydrogen. Now that we now need to figure out the weight of the oxygen. There's only one of the oxygens present, so it's going to be a total of 16 grams. There is the mass or molar mass of oxygen divided by the total molar mass of H2O, and that gives you 88.79%. Now the sig figs may vary depending on the periodic table. For this class, I always have you round it to a whole number. So realistically, this should have been 11% hydrogen and then 89% oxygen. You know you did this correctly if the total is roughly going to be equal to 100%. Now I raised my little comments about how to calculate each of these because I put it on the previous slide. So here is the total molar mass of H2O. It requires 2 of the hydrogens and then 1 of the oxygen. And then here is 18.0. And then we have 2 moles of the hydrogen. So then you find the mass of this one by itself, and that's going to be equal to 2.02 grams. And then 1 mole of oxygen and that's going to be equal to 16.0 grams. Now we simply take the subscripts to figure out the number of moles for each. So there's a 2 there, so it's 2 moles of hydrogen. There's an implied 1 there, so it's 1 mole of oxygen. Let's see another example. What is a percent composition, or percent by mass, of magnesium hydroxide? So you break it down by element, not by ion, but element. So there's 1 magnesium, there's 2 oxygen, because keep in mind parentheses, that's a times 2, so 2 oxygen, and then there is 2 hydrogen. So 2 times that hydrogen, that's 2. You then have to multiply each one of these by the molar mass. So that gives you 24 grams. There's 2 of the oxygens, so that's a total for element oxygen of 32 grams, and then a total for element hydrogen of 2 grams. Make sure to add all of these together, and that gives you the total molar mass, and which is 58. So divide each of these numbers by 58 times 100, and then that gives you your percent. Again, you want to go ahead and round it to a whole number. Don't worry about sig figs, and you know you did this correctly if it equals roughly to around 100%. It may not actually be 100%, it may be like 99.8% or 101%, and that's okay. Here's a super tricky one. This is TNT. Trinitrotoluene. Yes, this is dynamite. And in this first part, they go ahead and they figure out what is the molar mass. So that's the molar mass of the entire TNT species. And then they figure out the molar mass of each of the elements by itself. So for example, with carbon, there's 7 carbons. So you had to do 7 times 12.01, and then it gave you 84.07. So that is the total element mass for carbon. And then you do the next one for hydrogen. There's 5 hydrogen. So 5 times 1.01, 5.0 grams. And so that one, there is a mistake. Awkward. So this one over here should be 5.05 grams of hydrogen. I'll have to change that one. And then 42.03 for the next one. And then 96 for the last one. So now we're going to go ahead and finish up some other calculations you have to do. So going back to the front outline, we just got finished doing percent composition, also known as percent by mass, from the molecular formula. Now we're about to use that percent composition to find the empirical formula. So this is kind of a taste of what you can do with percent composition, what you will be using the percent composition for when you get into higher level classes. And yes, I could test you on this topic as well. Although in higher level chemistry classes, they go into much more detail. So we calculate empirical formula from percent composition, and then we're going to calculate the molecular formula from empirical formula. Afterwards, we're going to introduce hydrates, and then we're pretty much done, since we're not going into the calculations of hydrates. So let's go back to the slides. Let's go ahead and talk about the concept of empirical formula. It is the simplest whole number ratio of ions in a formula unit or atoms of each element in a molecule. That's a mouthful. So if I were to have a structure that looks like this, S2H8, and I would divide this 2 and 8 by a number such that it gives me the least whole number ratio, In this case, if I divide by 2 and divide by 2, I could end up with S1H4. S1H4 is the empirical formula that's taken from the original molecular formula or ionic formula. So let's do another one. If I have something like this, S9H12, then the largest number that is divisible into 9 and 12, resulting in a whole number, would be 3. So I divide the molecular formula in this instance by 3, and that gives me S3H4. Now I obviously couldn't use 4 or 5 or 6 because then I'll end up with a ratio. And as far as what I'm going to teach you, we're just going to stick with whole numbers. So taking C6H6, the number 6 is divisible into both, creating a whole number. So this right here, C1H1, where the ones are implied, is considered the empirical formula. And this one over here, if we divide both of these by 2, then we have C4H9. Now we couldn't divide it by anything else. If I divided by 4, then I would have ended up with a fraction for hydrogen. So the most I could divide it by is 2 for each, and this is the empirical formula. So now we're going to skip this part because I'm not going to test you on it. We're going to go ahead and use our percent composition, or percent by mass, same thing, to figure out what is the empirical formula. Now this is not a true molecular formula, but there's other techniques we can use to figure that out later on. So this gives us another piece of the puzzle. First thing we do is we turn the percentage into grams. Once we have the grams, so for example, the 92.2% is now 92.2 grams. The 7.83% is 7.83 grams. I then need to go ahead and turn this from grams to moles. And I have to use the periodic table molar mass as a conversion factor. So looking at my periodic table, at least the one I have, you divide it by 12.01 grams, and that gives you 7.68 moles. 7.83 grams divided by 1.0 grams, and that gives you 7.75 moles. You're then going to go ahead and divide by the smallest number. So the smallest number of the two is 7.68. And this, when you divide by the smallest number, or here's an example shown right here, that gives you the crude empirical formula. So C1H1. Now technically this is 1.01, but in this type of calculation this is considered good enough. So you would round to a whole number. So 1.01 is rounded to 1. So let's do some other examples. First thing I do is turn the percentage into grams. Next, I go ahead and use a periodic table to convert grams into moles. So on my periodic table, sulfur is equal to 32.1 grams, depending on which periodic table you have, but that's the one I used. And that's 1.25 moles. Oxygen is going to be 3.75 moles. I then divide by the smallest moles, in this case 1.25. That's what you see here. And then you'll end up with a 3:1 ratio. So in this case, it's going to be an S1O3, where the S is implied. So the more electronegative element is at the end of the empirical formula. I probably would take away points for that if you didn't do it that way. What I would take away points for is if you have the wrong subscripts on the empirical formula. So it's SO3. Let's do another one. What's the empirical formula? Based on the percent by mass, turn it into grams, divide by the molar mass, turn it into moles, figure out which one is the smallest moles, and divide each of these by the same one. In this case, it's high for 3.33. So 3.33, 3.33, 3.33, as you see there. And then we end up with a 1 to 2 to 1 ratio. So C1H2O. So make sure you know how to do that problem. And then here's another problem that you can work through. Now it is possible to have fractions. So in this case, this has a fraction, and I made a big deal about how I try not to have fractions, but there are going to be exceptions. So in this case, if you have a perfect 1.5, then you really need to multiply everything by 2, so that way you have a nice whole number ratio. So again, if you ever end up with a non-whole number, such as 1.51, then you need to multiply your final answer by 2 for each of these. Realistically, I probably won't give you one like 61. I don't like the extra step, but I definitely could give you one like 60 and 59. Slide 60 and 59. Now, what we can do is we can reason out what the molecular formula is from the empirical formula once we have that down. So, if we suspect it, we know what the molar mass is. So in this case, if my empirical formula is CH, and that's 13 grams per mole, and all I did was I added up 12 grams for carbon, 1 gram for hydrogen, and then that's the empirical formula molar mass. And then I figure out what is the molar mass of our suspected molecule, in this case benzene, which is 78 grams per mole. I simply divide the molar mass of the suspected molecule, what we think it is, divided by the empirical formula molar mass, and then whatever that new number is, the ratio based on the molar mass divided by empirical formula mass, that's going to be the multiplier for our final answer. So if our original empirical formula was C1H1, then this is a multiplier, and it multiplies each of these empirical formula subscripts, forming C6H6. So if I give you a molar mass of our suspected molecule, and then you have the empirical formula, you should be able to calculate the empirical formula molar mass, and then use that and divide the molar mass of our suspected molecule by the empirical formula molar mass. And then that'll give you the multiplier for figuring out the proper molecular or ionic formula. Yay. Alright, let's move on to the last topic. These are hydrates. These are any type of ionic compounds. So notice the metal and non-metal. And the non-metal happens to be polyatomic ion. That's another hint. It's ionic. So it's a ionic compound. It's a solid with water that is covalently bonded to it. So if I were to sit there and draw out copper sulfate, it would look like this right here. There's my positive copper. There's my sulfate that's connected. And again, they're neutralized each other out because they're really close. So there's my copper sulfate right there because they're neutralized. And then they would have these covalent bonds to water molecules. So this is copper sulfate pentahydrate because there's 1, 2, 3, 4, 5 water molecules attached. Now, they're attached to each solid copper sulfate, so technically all of this is considered a solid. Um, and anything that has a nice solid repeating structure we call a crystalline solid. So crystalline means like a repeating pattern. So technically you're holding solid water in your hands when you hold a hydrate present. So we usually will put a multiplier here and tell you how many water molecules are covalently bonded to it. Now we can, now if we want to, we can go ahead and heat it up, and when we do, we can actually remove the water molecules, and they can turn back into a liquid or a gas. Now, there's a lot of ionic compounds where it's reversible. So even though it lost the water molecules, when it cools down, it's possible for it to pick up the water molecules and have it go back into the copper sulfate. So we have these all the time in new clothing. You'll see tiny little plastic pouches, and it absorbs excess water moisture so it doesn't ruin the clothing. They tend not to use copper sulfate. They use some sort of silica instead. And we say that these are anhydrous compounds because they're there without water. We also call these desiccants as well. And without the water, they like the water, so they're ready to pick up any moisture and then have it covalently bonded and going the opposite direction. So if it has the water, we call it a hydrate. If it doesn't have the water, it's called an anhydrous compound, also known as a desiccant. Now there's calculations that I am not going to ask you to do, but here's a nice pretty picture showing you the before, where the blue substance is actually water molecules that are covalently bonded to the copper sulfate. And when we heat it up, all the water is, all the covalent bonds are broken and the water is released. And then that white substance is the anhydrous compound, also known as a desiccant. It's pretty cool because when you start putting drops of water on there, all the water disappears and you'll see the blue color start to form again as it forms the hydrate again. And everything still feels flaky as a solid, even though you know you put liquid water on there. It's kind of cool. So that ends this packet of slides. And ignore all the other calculations for percent hydrate. We're not going to be doing those.